Hi, friends. You're welcome to Assange Academy for Global Conquest. This is an e learning platform with rich content and candidate friendly or student friendly. I'd like you to subscribe and click the notification bell so that you will get notified each time new content is uploaded. We will be looking at momentum shortly. It's just a brief lesson. The momentum of the body is the product of its mass and velocity. It is the product of its mass and velocity. Momentum is mass times velocity, and the unit of momentum is kilogram meter per second because it is the product of the unit of mass and velocity. Momentum is the product of mass of a body and its velocity. Let us look at what examples. We have examples to do, and the first example says calculate the momentum of a 6 kilogram mass moving with a horizontal speed of 30 meters per second. Straightforward, we state our equation that momentum is equal to mass times velocity. The mass is 6, the velocity is 30. Therefore, the momentum is 6 times 30, giving us 180 kilogram meter per second. It went off. Okay, we are going back to this what example. This is the mass 0.3 and the speed is 30 meters per second. So we extract our parameters. The mass is 0. That's the mass and that is the speed. And what is momentum? mv. So 0.3 times 30 gives us 90. 0.3 times 30 with your calculator, you will have 90 kilogram meters per second. Uh, Read this. Then, if what if this arrow penetrates into an object and both move forward as one body with a common velocity? Can the common velocity be calculated? We just saw an arrow that was thrown, and the question is if this arrow penetrates an object, say a block, and pushes the object together with the arrow and they move with a common velocity, is it possible that this common velocity can be calculated? To appreciate this, I want you to look at this diagram. We have before collision and after collision. The arrow is moving with a speed of 30 meters per second and has a mass of 0. The block is at rest, so its speed is 0 meters. The block is penetrated by the arrow and the combined mass is 100.3 kilogram with a common speed. Now the question is, can we calculate this speed? This now brings us to the principle of conservation of linear momentum. What is the statement of that principle? That is what we're going to use to calculate this speed. In a collision, the momentum before is usually equal to the momentum after. And that is what we need to calculate problems that involve collision or impact or explosion. The principle of conservation of linear momentum states that the total momentum just before collision is equal to the total momentum just after collision, provided no external resultant force acts on the system. Provided no external resultant force acts on the system. When you are making a statement of the principle, don't ignore this phrase. Provided no external resultant force acts on the system, then the total momentum just before collision will be equal to the total momentum just after collision. Let us see how this law is stated mathematically. We have the sum of momentum before collision is equal to the sum of momentum after collision. This is summation sign, the sum. This sign means summing things together. If there are two bodies colliding before collision, their total momentum is equal to the total momentum after collision. Or this statement can be written as m1 u1 plus m2 u2 is equal to m1 v1 plus m2 u2. At least v2, at least you can now appreciate why I'm using v, initial velocity, final velocity. The initial velocity produces initial momentum, final velocity produces final momentum, initial velocity for m2 produces initial momentum, and final velocity also produces final momentum. This is just for two particles. Now let us go back to the arrow issue that we saw. We said the mass of the arrow is 0.3 and the speed is 600 meters. The mass of the block is 100 kilogram and the speed is 0 because it is at rest. The combined mass, the mass of the first and the second, is equal to 100.3 because the first one is 0.3 and the second one is 100. Now, from the principle of conservation of linear momentum, we have that the total momentum before collision is equal to the total momentum after collision. In calculation, we state it simply as the total momentum before collision is equal to the total momentum after collision. This is when you are calculating. You can simply state this formula like this. I mean this principle in this manner. But if you are asked to state the principle, you must indicate that the total momentum just before collision is equal to the total momentum just after collision, provided no external force acts. Now, if we state the formula, we're going to have m1 u1 plus m2 u2 is equal to m times v. This m, take note, is the sum. So this is 0.3 times 30 plus 100 times 0. I hope you know why 0. Because m2, which is the mass of the block, is 0. This is equal to the combined mass times the combined speed. 100 times 0 certainly should be 0. So that is why we have, look at what we have now. We have 0.3 times 30 is equal to 90, and 100 times 0 is equal to 0, and we bring down 100.3 V. Okay, what is V? V is equal to 90 divided by 100.3. It gives us 9.9 meters per second. Look at it again. M1 U1, M2 U2 is equal to M, which is the two masses times the common speed. Mass, initial speed, mass, initial speed, combined mass, combined speed. This one reduces to 0. This one gives 90, and we bring down this. So we make V the subject by dividing all through by 100.3. What do we have? Our calculator tells us that if we compute that, we will have 0.9 meters per second. Beautiful. What example number 3? A lorry of mass 2000 kilogram moving along a straight road with a speed of 15 meters per second has a head-on collision with a car of mass 1000 kilogram traveling in the opposite direction. On collision, both car and lorry lock together and come to rest immediately. It means after collision, they stick together and they come to rest immediately. 1. Calculate the momentum of the lorry before collision. 2. Calculate the speed of the car before collision. The momentum of the lorry before collision is mass times the initial velocity. Mass of the lorry times the initial velocity of the lorry before collision. So a simple substitution will give us 30,000 kilogram meter per second. Mass times speed. mass times speed. Remember, this is the initial speed before collision, and it gives this. Now, we have to calculate the speed of the car before collision. We will employ what? The principle of conservation of linear momentum. The momentum of the lorry before plus the momentum of the car before is equal to the combined momentum of the system, because they were locked together, so we add their masses. Unfortunately, they came to rest. Coming to rest means their speed is zero. Their speed is zero. They came to rest immediately. After substitution, we have mass times speed is 30,000. Mass times speed is 1,000 UC. Speed of the car is equal to, the left hand is zero, momentum after, the right hand is zero, momentum after is zero. So we carry this 30,000 across the equal to sign to this side, it becomes minus. We are left with 1,000 times UC. What do we get for UC? Come on, yeah. UC is minus 30 meters per second. Why minus? Because momentum is a vector quantity. I didn't want to tell you that because I wanted us to solve this problem. Then you will certainly be asking, why minus? Momentum is a vector quantity. Directions are important. Remember, the lorry was moving in a particular direction and the car is in a direction opposite. It says the car is traveling opposite. So what proves that it's traveling opposite? The speed is minus 30 meters per second, meaning its own momentum is minus its own momentum before collision is opposite to the momentum of the lorry. That is why we have minus 30 meters per second. Beautiful. What example number 4? I think this should be the last. What example? A 0.3 kilogram bullet is fired from a gun of mass 5 kilograms. The bullet moves horizontally with a velocity of 900 meters per second. Calculate the recoil velocity. If you have ever fired a gun, the experience is that when the gun explodes, as the bullet flies forward, the gun shakes backward. The gun recoils. Why? Because momentum must be conserved. Now, how do we calculate? We employ our principle. Each time there's a collision or an explosion, you immediately know that the principle has to be used. What does it say? Total momentum before collision is equal to total momentum after collision. Once you state it, you are already on the safe side. You are on the winning side. All you need to do is to know how to extract your parameters. After the worded expression, you should also be able to state it mathematically, where this is the momentum of the bullet, the momentum of the gun before collision is equal to the momentum of the bullet and the momentum of the gun after collision. If you state this very well, then you are already on the side of victory. What next do we have? We must look at the question and reason it out. How do guns operate? When you are about to fire a gun, you certainly hold it up in your hand and pull the trigger. So before you pull the trigger, what is at rest? The gun is at rest and the bullet in the gun is also at rest. So the speed, the initial velocity of the bullet is zero. The initial velocity of the gun is zero. The initial velocity of the bullet is equal to the initial velocity of the gun, which is zero. Why? Because before pulling the trigger, the gun is at rest and the bullet is also at rest. If this is true, then we are saying that before collision, the total momentum was zero. The left-hand side is zero. Okay, therefore the left-hand side is zero. We are left with the momentum. The left-hand side is zero. We are left with the momentum of the bullet and the momentum of the gun. Now, what we have now is mathematics. We send one the other side, it becomes minus. And when we solve for V, the velocity of the gun, by dividing through by the mass of the gun, we have minus 50 54 meters per second. What does this mean? It means that as the bullet flies forward, the gun recoils. As the bullet moves forward, the gun jerks backward. As the bullet flies forward, the gun recoils. So two of them are in opposite direction in order to balance up with the momentum, which was zero, so that they will cancel out and it becomes zero. Zero before should be equal to zero after. Some daily observations due to conservation of momentum. Number one, when a rifle or a gun is fired, it jerks forward as the bullet moves backward. Momentum is conserved. Number two, a rocket launched from rest moves forward as air rushes backward. If you ever observe a rocket as it's launched and is heading forward, flying forward, the air is rushing backward. Momentum is conserved. Number three, when a man jumps out of a boat, the boat is seen moving backward. Those of us who are used to jumping out of boats, I'm sure you must have experienced that. Even when you jump out of a tree, when you jump from the branch of a tree, as you are flying forward, the branch of the tree jerks backward. If you carry a little child in your arms and the child jumps from your laps, you will experience a push backward. Momentum is conserved. That's beautiful. And lastly, a balloon filled air rushes, or a balloon filled with air, sorry, rushes forward while the air rushes backward when untied. When you untie a balloon, you discover that the balloon rushes forward and the air rushes backward. Why? Momentum is conserved. Please, if you enjoyed this presentation, I'd like you to subscribe for more content and hit on the notification button so you'll be notified when next content is up. Thank you.